Alright, so welcome again in another tutorial of the topic differentiations. And in this tutorial we shall see differentiation as a rate measure. That differentiation can be used to measure the rate of change. Now let's say S is a displacement. So S is a displacement and T is time. And T is time. Let's say a body now moves from S, displacement of S to S1, okay, from T at time T. When it was S, it was time T, and when it reached S1, the time was T1. So the average speed is just S1 minus S over T1 minus T, which can also be written as delta S over delta T. This is what we call the average speed. Okay, as the body moves from time T1 to T. But this average speed now, as delta T now, the change in time, the limit of this average speed as the change in time approaches 0 is equal to ds dt. This now is what we call instantaneous speed. Nikisema instantaneous namaanisha the speed at a particular time. Yani kama time ilikuwa ni sekunde 25, speed ni ngapi? Ni tofauti kabisa na average speed ambapo nahitaji time interval kuanzia ngapi mpaka ngapi. Ila hapa ninachohitaji ni time to at an instant kupata speed. Ukitaka kuelewa hii mambo ya instantaneous speed, kumbuka tulivyosoma kwenye gradient of a curve. Tukasema dy dx ni gradient of a curve at a point. Hivyo na instantaneous speed is the speed at a particular time t. Kwamba t ikiwa ngapi, speed ni ngapi, ndio maana ya instantaneous speed. Sasa hii ni differential coefficient of s with respect to t. Na hii speed, so this is why we say the differential can as a rate measure. But also, what the change in velocity now, or the change in speed. Okay, let's say the speed changed from v. This v is called a speed or velocity. Let's call it velocity. So if the velocity changed from v1 to v at so it was t1, it's from v to v1 at time t to t1. So this now is the average velocity. I mean the average acceleration. This one is called the average acceleration. But if so usichanganye, hii ni average acceleration. I have repeated so many times, it's enough. So the limit now of this average acceleration as delta t now approaches 0 is what we call the instantaneous acceleration. Instantaneous. Kwa hiyo ni kama tu instantaneous speed, sema we are dealing with velocity instead of displacement now. Hii mambo mengine utakumbuka tu kwenye physics. So this one is what we call the instantaneous acceleration. Mark the acceleration at time t. Kwa hiyo kumbe differentiation sasa inatusaidia kupata instantaneous speed, lakini pia inatusaidia kupata instantaneous acceleration. Actually differentiation inatusaidia kupata the rate of change of any function at a particular point. The maana tunasema differentiation is a rate measure. It is used to measure the rate of a change at a particular point. Now let us see these examples. They will help us, they will enlighten us more. I'm going to write down this example, just bear with me. It says a body, call this example 1 for today. We say a body moves in a straight line. Moves in a straight line. A distance s meters. S meters in t seconds. So unaweza kuona s ni displacement, alafu t ni time. And s sasa tumeambiwa ni sawasawa na t cube. Let's say find the velocity and the acceleration of the body. So it says find the velocity and acceleration of the body. And acceleration of the body at t is equal to, at time 3 seconds. Maana anataka instantaneous velocity. So hapa mimi nina s sasa na t cubic. Kama anataka instantaneous velocity, najua instantaneous velocity is just ds over dt. Maana amesema at time t is equal to 3 seconds. Maana anataka at an instant where t is equal to 3 seconds. So this is just instantaneous velocity. Ni tofauti na angenipa time interval fulani. Lakini yeye amenipa at time t is equal to 3 seconds. Sasa hii manake ds dt, manake I just differentiate this. So I know for y equals to x power n, dy over dx is equal to n x n minus 1. So my n is 3, my x is t, so it's 3 minus 1. So it's just 3t squared. So this one now is the instantaneous velocity. So time is equal to 3 seconds. So I take just 3, I multiply with 3 seconds squared. What do I get? 3 times squared is just equal to 9. 9 times 3 is 27. So my instantaneous velocity will just be 27 meter per second. That way. So this one is instantaneous velocity. What about now instantaneous acceleration? So I know that instantaneous velocity was ds is equal to dt, which we have observed to be 3t squared. So instantaneous acceleration will just be dv over dt. But what is v? V is just equal to 3t squared. So this is just the same as I say 3 naweza nikaitoa nje because okay, this is just the same, ngoja niweke kwanza ndani 3t squared over dt, then 3 naweza nikaitoa nje kwa sababu ni constant, so dt squared over dt. So again I know that y equals to x power n, then my dy, my dx is equal to n x n minus 1. So my instantaneous acceleration now will just be equal to 3 times, this is t squared. So my n is 2 and my x is t, 2 minus 1. So this is just 2 minus 1 is 1, t power 1 is t, 2 times 3 is 6, this is just 6 t. So the instantaneous now acceleration will just be 6. I say at t is equal to 3 seconds. Again, I'll times with 3 seconds. This time no squared. So 6 times 3 will just give me 18. Acceleration is meter per second square. So differentiation as a rate measure, and hivyo ninavyofanya kazi. Just like that I have obtained the acceleration and the velocity after 3 seconds. Now let's check another example. Let me call this example 2 for today. It says that the diameter of an expanding smoke ring. So we have a ring that expands. Diameter of an expanding smoke ring. At time t is proportional to t squared. So the diameter of an expanding smoke ring at time t is proportional to t squared. Manake d sasa kama ni diameter is proportional to t squared. So asema if the diameter is 0.06 meter after 6 seconds, if the diameter nimeileta sasa na d is 0.06 meters after 6 seconds. 6 seconds. At what rate is it changing? Nataka nitafute rate of change. Hichi ndicho anachotaka nitafute. Maana anachotaka nitafute kimsingi ni dd over dt. This is what he wants me to look. So at what rate is it changing? So I know d is direct proportional to t square. So umesoma rate and variation from ngapi? From 3. So I know hiyo manake d is equal to kt squared, where k is constant. But when d is equal to 0.06 meters time is just equal to 6. So my k will just be equal to 0.06 over 6. This is just the same as 0.0. I'm sorry, here it's squared. So it's over 36. So my k now is just going to be the same as, if I divide here, I'll obtain 1 over 600. So this one is my k. You may just use your calculator. Okay, use your ES Plus calculator. You get 1 over 600. So what does this mean now? It means since we say d is equal to k over t squared, but we have obtained k to be equal to 1 over 600. So it means my d is just equal to 1 over 600 times t squared. So this is just the same as t squared over 600. So this one is my d is equal to t squared over 600. But what are we looking for? We're looking at what rate is the diameter changing. Okay, so I'm looking for d over dt. So I just have to differentiate this. Now if I differentiate this one, dd over dt, hii 1 over 600 ni constant, as usual naweza tu nikaitoa nje. So hii sasa nichukue differential ya huyu t square over 600. Kwa nishakwambia 1 over 600 ni constant, kwa naweza nikaitoa. Nitabaki na d t squared over dt. Again, y equals to x power n. So dy dx is just equal to nx n minus 1. So my n is 2, my x is t. So this is just be equal to 1 over 600 times 2. T, 2 minus 1. 2 minus 1 is 1, t power 1 is t. So this one is 2t. Divide by 2 is 1, divide by 2 is 300. So my dd now over dt is just equal to t over 300. Now hii sasa under the rate of change of d with respect to t. Sasa to conclude, ni hivi. Hiyo nishamaliza example 2. To conclude ni hivi. dy dx does not only measure the graph of a curve, the gradient, I apologize. The gradient of a curve at a point, or the gradient of a function at a point. No. dy dx also measures the rate of change of y with respect to x. Ndio maana tunasema differentiation is a rate measure. It means it measures the rate of change of a function with respect to x. So thank you very much. That's all about differential coefficient as a rate measure. See you in the next tutorial.